Now that we've defined cylindrical coordinates, let's now show how to evaluate the div, grad, curl, and the Laplacian in cylindrical coordinates. So now our objective here is to describe our del operator and operations involving del in cylindrical coordinates. And the first bit of information we need to know is how the base vectors relate to each other. And it turns out that they're related to each other through a coordinate transformation. So I hat is equal to cosine theta e hat sub r minus sine theta e hat sub theta. J hat is equal to sine theta e hat sub r plus cosine theta e hat sub theta, and k hat is equal to z hat. And again, this is you should refer to section 10.7 for change of basis. And this is essentially a rotation of coordinate system by angle theta. So again, returning to our original diagrams, with I hat in the x direction, j hat in the y direction, those are angled, those are directed differently from E hat R and E hat theta respectively by an angle theta, and hence the change of basis. So with that information, we can now relate del in Cartesian coordinates to del in cylindrical coordinates. So this is del in Cartesian coordinates, and substituting our relationship for our equation for I hat, we have cosine theta E hat R minus sine theta E hat theta for this first term. And then for the derivative with respect to x, so I'm going to now write d by dx. And so we can describe that using the chain rule in terms of derivatives with respect to r, theta, and z. So d by dx is equal to d by dr dx plus d by d theta dx plus d by dz dx. Okay, so the first term was I hat, the second term was d by dx, and we can proceed with the other terms. We then have the j hat term that we have to add, and j hat again was sine theta E hat R plus cosine theta E hat theta, and d by dy is equal to d by dr times dr dy. Again, we're applying the chain rule of calculus to show how y changes each with r, theta, and z. So we have d by d theta d theta dy plus d by dz dz dy. Again, this describes how y changes with respect to r, how y changes with respect to theta, and z, how y changes with respect to z. And then finally, the last term, which is simply E hat z times the partial with respect to r dr dz plus the partial with respect to theta d theta dz. And then finally we have, well, the partial with respect to z of dz dz. And this turns out to be 1. These all turn out to be 0 because r and theta do not depend on z. And then if we go back and remember the relationships between r and x, r and y, theta x and theta y, and substitute those relationships by use those relationships to determine these derivatives, it turns out that with a little algebra, we find that the del operator in cylindrical coordinates is equal to E hat r, derivative with respect to r, plus E hat theta times 1 over r, the derivative, partial derivative with respect to theta, plus E hat z times the partial derivative with respect to z. So this shows how we went from del and Cartesian coordinates using these relationships for I hat, j hat, and then of course k hat. And then we have these partial derivatives related using the relationships between Cartesian and cylindrical coordinates. And collecting these terms, we get this final equation for del in cylindrical coordinates. So now applying del in terms on a scalar field is simple. We just write that same operator and apply each term to the scalar field u. So this grad u is simply equal to E hat r du dr plus E hat theta times 1 over r partial u with respect to theta plus E hat z partial u with respect to z. And that gives the gradient in cylindrical coordinates. So for example, if we had a scalar field, u is equal to z squared sine theta over r, then grad u would be equal to E hat r, that's the E hat r component, and the derivative of this with respect to r is minus z squared sine theta over r squared, plus the E hat theta component times 1 over r, and the partial derivative of this with respect to theta is z squared cosine theta over r. And then we have our E hat z component, which is the partial derivative of this with respect to z, which would be 2z sine theta over r. And simplifying, we would get minus z squared sine theta over r e hat r plus e hat theta times, oh, let me write the base vector last. So we have z squared cosine theta over r squared e hat theta plus 2z sine theta over r e hat z. Now, let's consider doing the same in Cartesian coordinates. So in Cartesian coordinates, u would be described as z squared, and then sine theta, again, was y over r, and so we have a 1 over r squared, and that's equal to z squared y over x squared plus y squared. And this is a bit more cumbersome. To compute grad u in Cartesian coordinates. It's not hard to do. You just have to be careful, and you'll be using a bit more lead in carrying it out. So this is an example of a situation in which the gradient in cylindrical coordinates is quite a bit simpler to write out. Now let's consider the divergence in cylindrical coordinates. So the divergence of a vector, again, is written as del dotted with a vector. And writing out this del operator, we have, again, e hat r d by dr plus e hat theta times 1 over r d by d theta plus e hat z d by dz. And we're going to apply that like a vector dotted with vr e hat r plus v theta e hat theta plus vz e hat z. So I'm going to, so the first term has term 1a, 1b, 1c, and the second term has 2a, 2b, and 2c. So we're going to have to apply 1a to each of the terms in the second, each of the 3 terms in the second term, 1b to each of the 3 terms in the second term, and so forth. So we have 9 terms to evaluate. Let's look at the first pair, which would be 1a dotted with 2a. So here we have e hat r d by dr dotted with vr e hat r. And so we'll follow the rule that, so we don't know whether to apply the dot product first or the partial derivative first, but we'll follow the rule that we always apply the, we do the partial derivative and then the dot product. So we have e hat r dotted with the partial derivative of vr e hat r. And so that gives e hat r dotted with Now we have to, in general, remember the base vectors E hat r, E hat theta, E hat z, some of them change with r and theta. So we have to evaluate the partial derivatives of both terms here in general. So we have d by dr of Vr times E hat r plus Vr times the partial derivative of E hat r with respect to r. And in this case, E hat r does not depend on r. As r changes length, E hat r stays in the same direction. So in this case, this partial derivative is 0, and we are left simply with the partial of Vr with respect to r, E hat r dotted with E hat r, and this equals 1. So the first term gives the partial derivative of Vr with respect to r. Now let's consider the second term. So that was the first pair. The second pair is, well, let's consider another pair. It's not necessarily the second pair. It's another pair. And let's consider term 1b with 2a. And that is E hat theta 1 over r d by d theta dotted with Vr E hat r. And again, applying the derivative first before the dot product, this gives E hat theta 1 over r dotted with the partial derivative with respect to theta of Vr E hat r, and that's equal to E hat theta 1 over r dotted with the partial derivative of Vr with respect to theta E hat r plus Vr times the derivative of E hat r with respect to theta. And this is a case in which the base vector does change with theta. So for example, if we have our point here, again this is r, and this is E hat r at a given value of theta. If we look at another point, which is rotated by an angle d theta, then E hat r at theta plus delta theta is in a different direction. And it turns out the difference is parallel to the direction of increasing theta. So the let's see, I should say the difference is proportional to E hat theta. It's parallel to that direction. So this is equal to E hat theta. The rate, the partial derivative of r with respect to theta, that change is in this direction. It's in the E hat direction. So writing out this term, we have the first term is 1 over r partial Vr with respect to theta, and then we have the dot product between E hat theta and E hat r plus Vr over r times the dot product between E hat theta with E hat theta. And since E hat theta and E hat r are orthogonal, this term is equal to 0. E hat theta is, of course, equal to itself, so this term is equal to 1. So the final solution, the remaining term is VR over R. So that's what we get when we take the dot product of 1b with 2a. So after evaluating the remaining 7 terms, we finally get our divergence of our vector in cylindrical coordinates, which turns out to be 1 over r d by dr of r vr plus 1 over r dv theta with respect to theta plus dvz with respect to z. And this was a little bit more complicated to evaluate because, again, the base vectors in cylindrical coordinates depend on theta. So we had to evaluate those derivatives to get this expression. So if we were to, before we evaluated the gradient of a scalar field, so let's take the divergence of this vector. So we have our vector equal to the gradient of our scalar field, which was minus z squared sine theta over r squared e hat r plus z squared over r squared cosine theta e hat theta plus 2z over r sine theta e hat z. Realizing I wrote that on the wrong page, so let me paste that here. Okay. So the divergence of our vector is now equal to 1 over r times the partial derivative with respect to r of r times this term, which is minus z squared sine theta over r plus 1 over r times the derivative with respect to theta of this term, which is z squared over r squared cosine theta, plus the partial with respect to z of vz, which is 2z sine theta over r. And this is 1 over r. The partial derivative of this with respect to r is z squared sine theta over r squared plus 1 over r times the partial derivative of this with respect to theta is minus z squared r squared sine theta. And then we have the partial derivative of this with respect to z, which is just 2 sine theta over r. And you can see that this term cancels with the second term, and the final solution is sine theta over r. And note again that this is a divergence, so it's a scalar. The divergence of a vector is a scalar quantity, and it's equal to 2 sine theta over r in this case. So The other two important operators are the curl of a vector in cylindrical coordinates, and you would use the same reasoning that I went through to compute the divergence. I'm not going to go through that, but I'm going to refer you to page 785 for the divergence in cylindrical coordinates. And it's important to note it's not the curl of a vector in cylindrical coordinates is not equal to, for example, E hat r, E hat theta, E hat z, d by dr, d by d theta, d by dz of the vector. So don't try to do this in cylindrical coordinates because it'll be wrong. The last example is the Laplacian of a scalar, and that turns out to be the second derivative of u with respect to r plus 1 over r partial of u with respect to r plus 1 over r squared times the second derivative of u with respect to theta plus the second derivative of u with respect to z. And this is the Laplacian in cylindrical coordinates. And I encourage you, I'm not going to go through it now, but I encourage you to start with the example that we had where u is equal to z squared sine theta and verify that the Laplacian of u is equal to 2 sine theta over r. So our u is z squared sine theta over r, and I'd like you to verify that this is true. And the reason I know that this should be true is you might remember that the Laplacian of u is equal to the divergence of the gradient of u, and we just evaluated the divergence of the gradient on the previous page. So remember we had we took the divergence of the vector where the vector was the gradient of u. So I'll leave that for an exercise for you to carry out. Okay, so that covers these operations in cylindrical coordinates.